Hello and welcome to this section. In this section I will introduce univariate linear regression. Univariate linear regression uses one independent variable to predict one dependent variable, and there is a linear relationship between both. So basically the model assumes there is our target variable called y, and this can be explained based on an independent variable called x1. The only parameters that need to be estimated are the slope and an offset parameter. M is the slope parameter. It represents the impact of a change of 1 unit change of x1 on our target variable y. The offset parameter b, this bias term, adds a constant bias to the model. Effectively, this offset parameter represents the price that even would have to be paid if x1 would be 0. Then the second term in this equation is 0 and only b plays a role. Coming back to our simple housing market model, this would mean that we can create a formula for the price that takes the size into account. The size is multiplied with the slope parameter and the overall offset parameter is added. But what is actually the best fit or the best trend line describing our observation points? Here you can see observations for houses with different sizes and the corresponding price. In blue you can see different lines that should fit the data best. But which one is the right one? Let's find out. The slope represents the impact of a unit change of the independent variable on the dependent variable. That sounds actually very technical, but it is not that complicated. Since a change of 1 square meter is hard to detect, we choose here an increase of 100 square meters. The principle is the same. We take a measurement for our first observation point at 50 square meters. Here we have a price of 216,000 euro. Let's take a look at an increase of 100 square meters, so at a size of 150 square meters. So we increase x by 100 square meters, and for this observation we observe a price of 310,000 euro. Based on these two observations we can calculate the slope. The slope is the difference of both prices divided by the difference of size. In our case 940 euro per square meter is the slope. And the bias term b is found at the intersection with the vertical axis. Going through the 2 points we get our blue line. This would fit these 2 points very well, but not the other points. A much better fit would take all points into account. This is shown for the red line. So the algorithm takes a look at all model predictions and observations. It is enlarged here for one specific point. Usually there is a difference and your model does not fit the actual values perfectly. This is due to measurement errors or due to the fact that not all relevant parameters are taken into account. In our case, you can easily imagine that the size alone cannot perfectly predict the price. There are many more parameters like location, quality, and much more. So the model takes the difference of actual and predicted values into account, and these are then squared. This is actually done for all observations. All squared differences are summed up, and this loss function is minimized. So the best fitting line minimizes this function. This term is pretty much the definition of root mean squared error. This is the metric that is used for the minimization. And squaring the differences fulfills 2 different purposes. First, it handles positive and negative deviations identically. So overpredicting or underpredicting a price is the same for the loss function. And second, extreme deviations are punished more than small deviations. And you should always think about the assumptions you make and make sure that these assumptions are justified with the model. With linear regression, it sounds trivial, but the main assumption is that there is a linear relationship between the data. As we will see, higher order relationships are possible as well. You can check for homoscedasticity. This means if there are certain features in your data and your model does not represent these, there might be a pattern in the error plot. So you can plot the error, defined as the difference of actual and predicted values, versus the predicted values. And the main point to take away from here is that there should be no pattern in this plot. So all the points should be randomly distributed. Otherwise, you should rework the model and adapt it. In the next section, I will show you an interactive dashboard that you can also use and try yourself to find the best fitting line to a linear problem. That's it for this lecture. Thank you very much and see you in the next one.